Hello ladies and gentlemen, and welcome back for our third and final video on 3.4. We're going to show that these lines are in fact skew. The fact that they're calling them skew means that they must be in 3 dimensions, and the fact that they're skew means that they're going to be in some sort of arrangement so that 2 of their variables will be able to equal each other, but the third one will not, resulting in either maybe, let's say, the z variable was not the same, so it'd be on top of each other, or the x value is not the same, in which case one would be in front of the other, or something like that. You can use your 3-dimensional models to figure out how this looks. Okay, so the first thing that they're telling me that they're skew. Well, no, they're not. They want to show that they're skew, so we're going to expect that their direction vectors are not scalar multiples. Let's take a look. Consider direction vectors. So d1 is equal to 1, negative 1, 1, and d2 is equal to 2, 3, negative 1. If these are scalar multiples, then whatever I have to multiply this by to get that, I should multiply this by to get that, and multiply this by to get that. So that would have to be multiplied by 2. Multiplying negative 1 by 2 does not give me 3, so therefore d1 is not a scalar multiple of d2. Therefore, lines either have one point of intersection or are skew, in which case they have no points of intersection if they're skew. Okay, so looking at this, we now want to prove that they don't have a point of intersection. If they're skew, there is no point of intersection. But let's keep in mind that just showing that there's no point of intersection isn't good enough until we show that the direction vectors are not scalar multiples. Okay, so that's important. We need both. So now we're going to assume point of intersection exists. So we're going to make an assumption that it does exist. And when this occurs, at a point of intersection, x will equal x, y will equal y, and z will equal z. So, taking a look at our 2 lines for R1, I'm going to put them in parametrics. X equals 2 plus t, y equals 1 minus t, and z equals 0, 1t. For R2, we're going to get x equals 3 plus 2s, y equals 3s, and z equals negative 1, negative s. Careful that your s's don't look like 5s, otherwise everything gets confused. These are s's for me. All right, so at a point of intersection, for x equals x, you're going to have 2 plus t equals 3 plus 2s. So I take this x and I take that x and I put them together. Move things around. Maybe I'll do t minus 2s equals 1, and we'll call that equation 1. For y equals y, we're going to have 1 minus t equals 3s. I made the t positive, so I'm going to put the t over here. So it'll be positive t plus 3s equals negative 1. Hold on, let me see how I did that. So that comes over, so it's 3s plus t. That will be a positive 1. So be careful of that. When you're going to do things like that in your head, make sure you get them right. So that's a positive 1. And for z equals z, we're going to get t equals negative 1, negative s. Bring the s over. T plus s equals negative 1. So that's equation 2, and that's equation 3. They're what I call my elimination equation, so I'm going to use those. I can use any ones that I want. Why don't I start with x and x? This x equals x and y equals y this time. So I'm going to use 1 and 2. So I'm going to get t minus 2s equals 1, and t plus 3s equals 1. Well, look, the coefficients in front of the t's are there. And again, it's subtraction. It didn't need to be. But since the signs are the same, you subtract. When the signs are different, then you add. So it's t minus t, which is 0t, negative 2s minus 3s, so it's negative 5s, and it's 1 minus 0, so it's going, or 1 minus 1, which is 0, so s equals 0. Okay, that's fine. That's workable. We use this and sub it into either 1 or 2. Can't sub it into the third one. You need to leave that one clear to check for whether or not you actually have a point of intersection or not. So we got to leave that one clear, so we can go back into one of these two. Let's sub it into 1. So it's going to be t minus 2 times 0 equals 1. T equals 1. Wonderful. So the question is, do we actually have a point of intersection, or are we skew? So then check if point of intersection or skew. You're going to sub s equals 0, t equals 1 into equation 3. So this is the value of s, and this is the value of t that will allow x to equals x and y to equals y. The question is, at those values of s and t, does z equal z? If it does, grand. If it doesn't, then we got to talk about that. Let's take a look. So it's going to be 1 plus 0 equals negative 1. 1 equals negative 1, and you know that's not true. So what does this mean? This means that the math here is wrong. This can't be true. I haven't done anything wrong in the math here, so something must be wrong above that. There's nothing wrong in here, so something must be wrong above that, and there it is. I assumed a point of intersection exists. This says that there's a flaw in that logic. There's a flaw in the logic throughout this argument. The only place where there can be a flaw is at this assumption, so therefore, assumption is wrong, and no point of intersection exists. Therefore, lines do not have scalar multiple, direction vectors, and no point of intersection. Therefore, they are skew. There you go. All right. Here's your homework, textbook, correction to the textbooks. Make sure you take a look at them, and I'll see you guys on Wednesday. All right, guys, make sure you go through this, help each other, know your stuff. I'll take up homework questions on Wednesday. Bye-bye.